I just thought of starting with a small comment that it's exactly almost 100 years ago that for the first time we realized that Milky Way and Andromeda are actually two different systems, because previously we used to think anything that we are observing in the sky resides within the Milky Way. But then Hubble in 1925 approximately, based on Leavitt's relation and data collected by Charles Messier, William Herschel and others on Cepheids and nebula and other data, he basically showed that Andromeda is at a distance of 250 kiloparsec. The value was wrong, but it was large enough to basically tell us that Andromeda is a system in itself. And then he also found out that there are more systems which reside outside the Milky Way, so just exploding the expanse of the universe as we know it. I just thought of mentioning it because there's lots of enthusiasm about variable stars in the audience. I, on the other hand, I neither do variable stars nor do I study distant galaxies. So far I've only focused on the Milky Way, primarily using the Gaia data to understand the galaxy formation, for instance. So I'll be talking about these two substructures that we have identified in Gaia DR3 that you can see over here, and just trying to understand their properties, their nature, and their origin. So the outline is pretty straightforward. First, the context, so galaxy formation, and on the brief account of the orbit abundance space. Then I'll move to our analysis, which is basically identifying these substructures in the orbit metallicity space, and then further studying them using the abundances from apogee, and then finally just trying to understand the nature of these substructures. So, of course, one of the focuses of the community is to understand how the galaxy formed. So we are interested in really knowing ambitiously every single event that led to the present day, how the Milky Way is. And this includes trying to trace possibly every star formation that occurred, mergers, et cetera, et cetera. And all we have is the present day snapshot of our galaxy from Gaia, apogee, and all the other data sets that you can think of. So one way to do this is to have these observations and then map them in the age orbit abundance space, because that precisely tells you which stellar population formed where and at what time. But we know that ages are difficult to determine for most of the stars. So we are largely left with computing orbit, and with the abundances, we can map the stars in the space, which in itself tells us quite a lot about these various galactic events. So for instance, if you look at the orbit metallicity space, one of the common understanding that we are aware of is that most of the metal-rich stars, so stars with metallicity more than -1, lie along disk-like orbits. So these are the stars which you can see over here. And then most of the metal-poor stars, so stars below -1, have halo-like orbits. So the first category, we interpret them as being in situ, so maybe primordial gas settled into the disk. And then they have these circular orbits restricted within the disk. And then you have the halo-like orbits, which have varied eccentricity, inclinations, and so on, which coincides with our understanding that mergers also come along eccentric and inclined orbits. So they would have been originated because of these merging events. But this common understanding doesn't necessarily hold in all the scenarios. So for example, we know that there's an exception of a metal-rich population which actually have halo-like orbits. So this is the so-called splash population, which you can see here. So these are relatively metal-rich stars, but on halo-like orbits, which one of the interpretation is that maybe they got perturbed. They're actually disk stars, metal-rich disk stars that got perturbed because some massive merger fell in and it perturbed, and stars got halo-like orbits instead of disk-like. Then you also have metal-poor stars, which actually have disk-like orbits. So we heard about Icarus in the morning, but I mean the metallicities, you have many other populations as well, Icarus, Atari, and others. And these populations have disk-like orbits, and they go all the way down to -2.5 metallicity and below. And instantly, we are interested to know, is it in situ population or are these accreted populations? But the answer is not so clear, as we know. Then that was the orbit metallicity space. Now I'll move to the abundance space, for instance. And so one of the common understanding comes is that We have the metal-rich population tends to be also rich in the abundance, and then you have the metal-poor population, which tends to be poor in the abundance as well. So schematically, I'm showing you this here. So you can think of the Milky Way thick disk, which is relatively metal-rich and is also enhanced in alpha abundance, aluminium, etc. And then you have the accreted population, be it dwarf galaxies or mergers, which are relatively metal-poor, but also depleted in most of these, if not all, in most of these elements. So this is just schematic, but we have seen these plots from Apogee and other surveys as well. So here I'm showing, you can see this is metallicity versus aluminium and magnesium. So you're seeing the four well-known dwarf galaxies and also GSE. So what's shown here is basically you see the thick disk, which is relatively metal-rich, but all of these dwarf galaxies and GSE basically are relatively metal-poor and also kind of depleted, at least in these two elements, and also other elements, some of them. One interesting thing to notice is that almost no stars in these dwarf galaxies have aluminium more than 0. So the aluminium, they're really, really depleted in aluminium abundance. And this will become also important when I talk about my own analysis. So please try to remember this. Those were the dwarf galaxies particularly. Here I'm showing you the mergers, Heracles, GSE, Sagittarius, Helmi streams. And the properties that's mentioned above basically holds for these mergers as well as for dwarf galaxies. That they are metal poor and somewhat depleted in the abundances, and almost no stars with aluminium over Fe more than 0. But again, this understanding also doesn't necessarily hold in all scenarios. So we know of the so-called poor old heart or aurora substructure, which has metallicity below -1, but is enriched in the abundances, for example, in the aluminium and magnesium abundance, which you can see here, and it has significant number of stars which are enriched in aluminium. So this would probably go somewhere here on the schematic diagram. And then instantly the question would be, okay, so this is in situ and this is accreted, so what is this? So if I can say something which is probably outrageous, but if I say that metallicity, if it roughly traces time, so something that's more metal poor would have formed very early on, and if magnesium and aluminium or other abundances roughly trace the mass or density of the progenitor, because I mean, if something is enriched in these abundances, maybe the progenitor was massive or dense enough to have probably pressure cooked these elements, and so that it could be enriched compared to accreted galaxies, which are probably low in mass and density, so they could not get enriched in these abundances. So then maybe these populations are resulting from some massive progenitors, but was it Milky Way or was it something else? So if you look at the simulations of galaxy formation, they basically point out that the proto-Milky Way, so I'm now drawing your attention towards maybe 12 billion years ago or so in the pre-disk era, when the galaxy was just about to be formed, so I'm talking about the proto-Milky Way, was actually formed by the coalescence of very massive progenitor systems. So they just came in to form the proto-Milky Way. So one of the questions is that at that point of time, what was really in situ and what was really accreted when the proto-galaxy was being formed? And maybe these enrichments that I previously showed you is basically pointing towards those old progenitors, which were old enough to be low in metallicity, but maybe massive enough to be enriched in these elements. But of course, this is an interpretation. This is one of the possible interpretations. So then you could also ask that, can we find more of such POH or aurora-like populations, or it's just one that exists? Right, so that was the context that I was just setting the ground for the upcoming slides. So when we started our analysis, our starting objective was really simple, not so complicated. It was just to look at the Gaia DR3 dataset and see if we can find some new substructures, for instance. So this is the Gaia DR3. So we started with the Gaia DR3 RVS dataset. So we have the 60 phase space information, and also metallicity for most of these stars, which are basically coming from data-driven estimates of BPRP spectra. So in total, we start with 6 million bright stars, which have metallicity uncertainty less than 0.1. So the metallicity estimates of these stars are quite robust. Then if we only look at one of the ways, as I mentioned before, to look for substructures is to look in the orbit or orbit metallicity space. But if we only look at the LZ energy space, so we see this, you see the disk and maybe some component of the halo. But in the next slides, I'll basically slice this diagram in bins of metallicity. So if we first look at the metal-rich bins, so the disk, this dense feature that you're seeing, it's a thin disk, for instance. Then if we move towards a bit more metal poor, then we see the thick disk, and the so-called splash population also appears, as I was previously mentioning. Now, if we go more metal poor, we see the two previously known overdensities, which is the GSE over here, and it's the poor old heart or the aurora that you see over here. But we also spotted these two overdensities, which we are then calling Shakti and Shiva, for instance. So these occur between, very obvious to note, between -2 and -1 metallicity range, but in principle they go all the way down to -2 and below, for instance. But so basically we're interested in analyzing now Shakti and Shiva, for example. So this is the distribution of these stars in the galactic, in the galaxy. So they have an epicenter of about 8 kiloparsecs, so they are really distributed just within the solar radius. They have a Z max of 3 kiloparsec, moderately eccentric, so they have a range of, they possess a range of values in eccentricity, and each of these substructures have a mass of about 10 to the 7 solar masses. So this is just a very crude, rough estimate. Then we cross-match it with the apogee data, and you're seeing this FEH versus Mg and FEH versus, I mean, aluminum and magnesium abundance over here. So both of them are actually enriched in magnesium and aluminum, and they are nearly half of the sample of these substructures basically are enriched in aluminum as well. So they seem to have abundances like the PAOH or aurora, for instance. At this point, I also want to mention that people probably interested in bar would know that, I mean, it has been proposed that these overdensities may also be the result of halo, some of the stars being spun up by the rotation of the bar. So these spun up stars would end up having higher angular momentum values, which can result in this shape that you're seeing here that was highlighted in one of the papers. But I'll just say that Shakti seems to have higher angular momentum value than the proposed rich component. And also, if it's really the halo that's spun up, then you expect the Shakti to have abundances similar to GSE, which is not the case because Shakti has different abundances than GSE, for instance. Happy to discuss this also in the discussion section. So then this is probably not the scenario that very well explains this. Then if I just focus on the properties that we have learned so far about these two substructures, one is that they are really high contrast overdensities in the LZE space and in the metal poor regime. So this is generally, we understand it to be, if something is coherent in the orbit space, they were probably formed within distinct potential wells, and that came in the Milky Way, and they occupy a smaller space in the orbit metallicity space. The orbits are somewhat halo-like, and probably massive progenitors, but then they are enriched in magnesium and aluminum. So if I try to weave in these arguments together, one of the possible interpretations could be that perhaps these two are two of those massive progenitors that came in very early on to form the proto-Milky Way, for instance. But if this is really the case, then I'm also wondering if is it possible for such early progenitors that probably came in 12 or 13 billion years ago to remain coherent in the orbit space till present day, for instance. So I do not know what cosmological simulations or other simulations say about that, but that's something I'll be interested in. And with that, thank you for your attention.